Okay, so today will be the last day with new material. We'll have one more class period where we do a Socrative type review before the final. But let me talk to you a little bit about the big picture. So we'll do that by looking at the 5 postulates of quantum mechanics, and most of these will be familiar, but there'll be a few added details. But otherwise, it will serve as a reminder to kind of give you a big picture. And then we'll take a look for a little bit at postulate 5, which is one that we really haven't touched on at all, and that's the time dependence of the Schrodinger equation. Okay, so postulate 1, it will be familiar. This is basically the Copenhagen interpretation of the wave function. The state of a quantum mechanical system is completely specified by a function psi of r and t, so position and time, that depends on the coordinates of the particle and on time. Notice it says particle. This function, called the wave function or state function, has a property such that psi star psi dv is the probability that the particle lies in the volume element dv located at r and time t. Okay, so I emphasize here that this thinks of the system as a particle, which we often do, but this is a little bit inconsistent because we do sometimes talk about it as a wave, and we do explicitly talk about wave-particle duality. And this was actually a big debate back in 1927 at the conference in Copenhagen, where Born and his student Heisenberg really were proponents of this interpretation. But Schrodinger and Einstein really didn't think that this was all there was to it, and preferred to think of the solutions to the Schrodinger equation as waves. And I think we've come to a more mature understanding now where we know that actually both are true, that the system is going to be both a wave and a particle at the same time, and thinking of it as sort of a crest of a wave where it has a higher amplitude in some spaces than others is kind of equivalent to thinking of it as a particle with a large probability in some spaces compared to others. So the probability of a particle versus the amplitude of a wave, those are kind of two sides of the same coin. Schrodinger and Einstein thought of it as amplitude of a wave, and Born and Heisenberg thought of it as a probability of a particle in a certain space. So anyway, if you're curious to learn more about that, I did post, I just came across it as I was cleaning out some files, a paper that I wrote for a history of science class, interim class back in 1995 when I was a student at Calvin. So you can look at that on Moodle. All right, postulate 2. For every observable in quantum mechanics, there corresponds a linear Hermitian operator. For every observable in classical mechanics, there corresponds a linear Hermitian operator in quantum mechanics. Okay, so the operators, this is from Macquarie's Quantum Chemistry, 2nd edition. So I like this book, but I don't want to make you guys buy a new book. But anyway, it's a good book. If you're going into PChem, you might want to consider getting that for your birthday or something. But it has here a table of all of the operators that we've been dealing with, and what their symbols are and what you actually do. So for x, the symbol is x hat, you multiply by x, etc. We've got momentum here, you take a derivative, kinetic energy, you take a second derivative in 1 dimension or 3 dimensions, potential energy, just multiplied by the potential energy. Total energy, it is the Hamiltonian, so you've got your kinetic and your potential part. And then the angular momentum are these kind of cross product type of derivatives. So those are the different operators that correspond to classical observables. And then Hermitian just means this. So f star a hat f dx will be equal to f a star a hat star f star. And this didn't really come into play in all the different calculations that we did, but this Hermitian property is important for for proving some of the things that need to be proven to do all the quantum mechanics calculations that we did. So anyway, don't worry about it too much, but some of you have come across that in some advanced math classes, I think. All right, postulate 3. In any measurement of the observable associated with operator A hat, the only values that will ever be observed are the eigenvalues, which satisfy the eigenvalue equation. A hat psi equals A psi. Now, of course, it won't always be an eigenfunction of every observable, so sometimes we can't observe certain things, like we can't observe the position of a particle in a box, for example, but we can observe the momentum. And this is related then to postulate 4. For sometimes we can't observe the observable, but we can find the average. We can always find the average. So if you can sandwich the operator between psi star and psi, then you can find the average in this way. And we've done that a lot. So that's where we spent most of our time, postulates 1 through 4. Let's briefly today look at 5. So the wave function or state function of a system evolves in time according to the time-dependent Schrodinger equation, and here it is. H psi of xt is equal to I h bar d psi dt. Okay, take this as a postulate. I won't justify it for you here. But if we take that as a postulate, then let's do a little bit of calculation, and this will be our only new material for today. So the time-dependent Schrodinger equation, I've just rewritten it here. The Hamiltonian does not depend on time. You can see that in the table here. Yeah, it's just about space, unless, of course, the potential were changing with time or something like that. So in general, we'd say the Hamiltonian doesn't depend on time. And this derivative over here, this is a partial derivative with respect to time, so it does not contain any information about position. Now, if we can separate our variables into two functions, psi of x, f of t. Now, this is probably a good approximation, but it's probably not strictly true. But if we could do that, separate our wave function into a function of x multiplied by a function of time, then we can think about substituting this in. If we put it into here, then the position part would stay, the time part would slide through. Similar over here. The position part would slide through, but the time part would stay. And then if we divide both sides by psi xt f of t, then the time part cancels from the left-hand side, and the position part cancels from the right-hand side. So this whole left-hand side depends only on x, and the whole right-hand side depends only on t. We also know from the time-independent Schrodinger equation that h psi equals e psi, so we can plug that in, substitute that in here, and the psi will cancel, and this whole thing, which is equal to this whole thing, is equal to just e. Okay, in other words, since this depends only on t, I can get rid of the partial and replace it with a full derivative with respect to time. And then doing some rearranging, df dt is equal to negative I over h bar e f of t. The negative comes from the fact that I had 1 over I, and then you can put I in the numerator and you get a negative. This can be solved, and you get f of t is equal to e to the negative e I e t over h bar. So in other words, psi of xt, just substituting this in now, right here, is just equal to psi of x times e to the negative I et over h bar. So now in general, what actually happens is you have all of these different x's, all these different psi's, which will have different e's, so we can sum over all of the stationary states, all of the eigenstates of the function, and e to the negative I ent over h bar. In other words, the time in the system lives in the superposition of all of the stationary time-independent states. And we have here another sum over states, much like we have in statistical mechanics, which is kind of interesting. But the way that the system evolves in time is basically these little c's, these coefficients will become smaller or larger as the system moves from one state to another. So really the way to think about the quantum mechanics of the system is that it's probably all the time in a superposition of all states, all stationary states, but sometimes it'll be almost fully in one state or another. So all these CNs will be 0 perhaps, except for one of them will be 1. Then it would be fully in just one of the stationary states, or it could be in a mixture of many states. And this gets us back to Schrodinger's cat, where the cat is in a superposition of both the alive and the dead states as a function of time, and that will depend on the energy of the two states. So if the dead state is much lower in energy than the alive state, then that one would be more likely to be occupied at that moment in time, because e to the negative large number would be small. And there you have it. All right, that's it for new material for this semester. Whew. Too cool. Quantum mechanics is awesome. All right, and we'll do some review tomorrow.